It is September 1978 and Hurricane Ella is churning up the Atlantic. Just listen to this emergency broadcast as
62.6 west, moving towards the west-northwest at 29.
The storm barrels toward New York City. Thousands of tenants inside the brand new Citicorp Center work their normal shifts. They are entirely unaware that their skyscraper is secretly at risk of collapsing in high winds. Hidden behind temporary walls, a desperate midnight repair job is underway. Frantic welders are reinforcing the structure while the city sleeps. This unfinished operation could mean the difference between survival and catastrophe. The crisis in 1978 was the terrifying climax of an architectural gamble that began years earlier. When banking giant Citicorp planned a massive new headquarters in Midtown Manhattan, they hired renowned structural engineer William LeMessurier. The proposed site on Lexington Avenue was perfect, except for one massive obstacle. St. Peter's Lutheran Church occupied one corner of the block. The congregation owned the land and flatly refused to relocate. They eventually agreed to let Citicorp build a new church on the same spot and construct the skyscraper over it. However, the church laid down a strict, non-negotiable condition. No structural columns could pass through their new sanctuary. Building a 59-story skyscraper directly above a freestanding church required a radical solution. Traditional skyscrapers rely on load-bearing columns at their corners to anchor the structure. Because the church sat directly under one of those crucial corners, LeMessurier could not put a support pillar there. Instead, he elevated the entire tower on 4 massive 9-story stilts. To avoid the church entirely, he moved these stilts away from the corners and positioned them at the exact center of each of the 4 sides of the building. This daring design left the corners of the tower completely unsupported from below, essentially letting the building overhang the church. To keep the skyscraper standing, the immense weight of the structure had to be aggressively redirected. If you look closely at the exterior of the Citicorp Center, you can see the visible consequence of this compromise. Built into the frame are giant diagonal steel chevrons stacked in 6 separate tiers. These huge inverted V-shapes span the entire height of the tower. They act as massive architectural funnels, catching the downward force of gravity and the lateral force of the wind. Instead of traveling straight down, the loads are driven away from the floating corners, pushed across the diagonal beams and channeled safely into the 4 central stilts. It was a brilliant feat of engineering, but it set the stage for a catastrophic hidden flaw. Those giant chevron braces perfectly handled the downward pull of gravity. But tall buildings face another relentless enemy, the wind. Broad skyscraper facades act like massive sails. As powerful gusts slam into them, the steel structures naturally bend and sway. Citicorp Center, however, was unusually light for a tower of its size. Elevated on those 4 central stilts, it was dangerously sensitive to high-altitude gales. Just listen to what wind can sound like hundreds of feet in the air. To stop office workers from getting seasick, LeMessurier incorporated a bleeding-edge piece of technology hidden right near the roof. He installed a tuned mass damper. This secret weapon was a 400-ton block of concrete floating on a remarkably thin film of pressurized oil. Whenever the wind pushed the skyscraper one way, a system of computer-controlled hydraulic arms instantly shoved this massive weight in the exact opposite direction. By constantly shifting its center of gravity to counteract the motion of the wind, the damper effectively neutralized the sway of the entire tower. It was an elegant, futuristic solution that reduced the building's movement by a staggering 50%. But relying so heavily on a largely experimental mechanical device meant the overarching structural design was pushed to the absolute edge of modern engineering. The tower was brilliantly balanced, but that extreme efficiency stripped away the traditional margins of safety. Older, heavier skyscrapers relied on thick steel and redundant pillars to survive storms. Citicorp Center relied on math, a floating block of concrete, and perfectly welded joints. By pushing the limits of modern architecture so aggressively, LeMessurier unknowingly set the stage for a catastrophic vulnerability. In 1978, an undergraduate engineering student named Diane Hartley was studying the Citicorp Center for her senior thesis. She contacted LeMessurier's firm with a surprisingly simple question. How did the building hold up against quartering winds? These are powerful gusts that strike the corners of a structure diagonally rather than hitting the flat sides straight on. At the time, New York building codes only required engineers to calculate for perpendicular winds, which LeMessurier had meticulously done. But the Citicorp Tower was unique because it sat on stilts positioned at the center of its four sides instead of its corners. A diagonal wind strike put unprecedented aerodynamic stress directly on those giant chevron braces. Intrigued by the students' inquiry, LeMessurier decided to run the new calculations for quartering winds himself. The math quickly revealed that diagonal gales increased the strain on the building's structural joints by a staggering 40%. Initially, LeMessurier assumed the tower could handle the extra load because his design explicitly demanded incredibly strong, fully welded joints. Then came the horrifying discovery. Upon reviewing the construction logs, he realized the steel contractor had made a critical alteration without his direct knowledge. To save money and labor costs during construction, the builders had completely scrapped the specified welded joints, swapping them out for standard bolted connections instead. Bolted joints were perfectly legal and common in traditional skyscraper construction. They were simply inadequate for the extreme loads of the Citicorp Center. When LeMessurier combined the weakened bolted connections with the newly calculated strain of a quartering wind, the structural integrity of the tower completely evaporated. The math was absolute. If a powerful enough storm hit New York, the bolts would shear off, the chevron braces would fail, and the 59-story skyscraper would collapse directly into the densely populated streets of Manhattan. LeMessurier returned to the original wind tunnel data to understand exactly how much danger the Citicorp Center was in. The numbers were chilling. He realized that neither the quartering winds nor the bolted connections were fatal on their own, but combined, they created a perfect disaster. His calculations showed that a quartering wind of just 70 miles per hour could generate enough force to snap the structural bolts entirely. There was still one theoretical fail-safe. The building possessed a 400-ton tuned mass damper designed to reduce wind sway. But as LeMessurier reviewed the system, he spotted a fatal flaw. The damper required a constant supply of electricity to function. A hurricane strong enough to threaten the building with 70 miles per hour winds would almost certainly knock out the local power grid. The very storm that would push the skyscraper to its breaking point would instantly disable its main defense. The stakes were unprecedented. Without power, the damper was useless. Without the damper, the bolted joints would shear under the extreme wind load. If those chevron braces failed, the tower would not collapse straight down into its own footprint. It would topple over sideways. Engineers calculated that a localized domino effect collapse would crush multiple surrounding city blocks under thousands of tons of steel and glass. If this catastrophic chain reaction occurred during a busy New York weekday, up to 200,000 lives were theoretically at risk. LeMessurier took his terrifying findings directly to Citicorp executives. Rather than burying the problem, the bank immediately agreed to finance a massive repair. They teamed up with city officials and structural engineers to hatch an unprecedented emergency reinforcement project. Above all else, the operation had to remain completely hidden from the public to prevent mass panic. Behind the scenes, the preparations resembled a covert war room. The city quietly coordinated with the local Red Cross chapter, tasking them to draft a staggering evacuation plan covering a 10-block radius around the skyscraper. To protect the building's only remaining defense, disaster response teams scrambled to secure a fleet of backup generators. These would ensure the tuned mass damper stayed powered even if a major hurricane knocked out the entire Manhattan electrical grid. Meanwhile, the permanent physical fix required manual labor on an immense scale. Engineers calculated they needed to weld heavy 2-inch thick steel plates over all 200 bolted joints to restore the tower's integrity. To maintain absolute secrecy, the repair schedule was flipped upside down. Every evening at 8 p.m., long after the office workers went home, specialized carpenter crews moved in to tear down the drywall covering the internal structural columns. Then, the midnight welders arrived. Working frantically through the dark, they fused massive steel reinforcements directly onto the vulnerable chevron braces. Before sunrise, the entire process reversed. The welders packed up their heavy equipment and carpenters rushed to install fresh drywall, vacuuming up the dust and hiding the night's progress. By the time morning commuters arrived at their desks with their coffee, the offices looked completely untouched. The daytime occupants remained blissfully unaware that they were sitting inside a fragile skeleton undergoing emergency battlefield surgery. But this delicate midnight choreography was suddenly interrupted by the very nightmare LeMessurier had feared from the beginning. In early September, Hurricane Ella formed in the Atlantic and began barreling up the eastern seaboard, aiming straight for New York City. At that exact moment, the secret repairs were only halfway finished. The night crews had successfully reinforced enough of the skyscraper to make it significantly stronger than it was when the structural flaw was first discovered. But the building was still deeply vulnerable. If Ella made landfall as a major storm, the sheer force of its quartering winds could easily overwhelm the remaining unwelded bolted joints, bringing the 59-story tower crashing down into the densely packed streets of Midtown Manhattan. Inside the covert command center, the tension became suffocating. Executives, city officials, and engineers were glued to updates from the National Weather Service, tracking every minor shift in wind direction and barometric pressure. The massive Red Cross evacuation plan was prepped, with disaster teams holding their breath, ready to trigger the alarm at a moment's notice. They could only watch the radar and pray the partial welds would survive the impending stress test. Then, the city got incredibly lucky. Just as Ella approached the critical danger zone off the coast, atmospheric currents shifted, the hurricane stalled, banked sharply to the east, and veered harmlessly out into the open ocean. The collective relief from the engineering team was immeasurable. The storm had passed, New York was spared, and the night crews safely concluded the remaining repairs over the following weeks, permanently securing the tower without the public ever knowing how close they came to disaster. The secret held until a 1995 New Yorker article exposed the truth. Modern reassessments by NIST actually suggest the building was in less danger than William LeMessurier calculated, yet his legacy is not a mathematical mistake. It is his choice to risk professional ruin to prevent a potential catastrophe, rather than hiding it. If you value deep dives into engineering history, subscribe to the channel. Thank you for watching, and please share your thoughts in the comments.